Hello and welcome on the talk on how to obtain high quality results with FLEUR. My name is Gregor Michalicek and I will present this topic to you. So in detail, I will first discuss how to set certain parameters that enter a FLEUR calculation. Then we will discuss certain challenges that come up when performing FLEUR calculations. For example, we discuss what happens when there are ghost bands and how ghost bands look like. Then we will discuss the linearization error, and finally I will conclude the talk. So let us start with setting the parameters. So the most important parameter that has to be set in a FLEUR calculation is Kmax. So that is the reciprocal plane wave cutoff. It turns out that this cutoff parameter is interconnected to certain other parameters. For example, to Lmax, so this L cutoff in the muffin-tin spheres, and also the L non-spherical depends on Lmax. So now let us assume a Rayleigh expansion of the plane wave at a muffin-tin sphere boundary. So I gave the equation for this Rayleigh expansion here. And actually this expansion expresses the plane wave in terms of spherical harmonics times spherical Bessel functions. And here in this panel on the lower right, I actually plotted these spherical Bessel functions. And you see that there is a rule of thumb of how we should select Lmax and Kmax and muffin-tin radii relative to each other. So the Lmax should be Kmax times the muffin-tin radius. Now let us have a look how this looks like in this panel. So if we assume that we have a muffin-tin radius of 2 and a Kmax of 4, then we have to choose an Lmax of 8. So essentially we are at this point here. So this purple line actually is the L equals 8 component for the spherical Bessel function, and you see that it is about at half of the maximum, and this is more or less always the case independent of how you choose the Kmax and the R muffin-tin. So we are at half of the maximum of the first maximum. So this actually means that our plane wave also contributes finite values to L components that we don't cover. So we have in our muffin-tin sphere the sum up to Lmax that gives our representation there. And of course, if we cut it beyond this value, then all these contributions that come below there for L equals 9, 10 and so on are not covered. So we have discontinuities at the muffin-tin sphere boundaries. So this is something that you should keep in mind. Also, the determination of the Kmax value is typically based on your minimal muffin-tin radius in the unit cell. And the non-spherical Lmax, so the reduced Lmax cutoff for the contributions of the non-spherical part of the potential to the Hamiltonian is calculated like this. At least this is about how you should choose it. Now let us have another look at some constraints on our choice of the Kmax value. So of course this is a cutoff parameter, and here I show you how the calculation behaves if I increase this Kmax cutoff. So actually you would expect that we are solving a variational problem, and then if we increase the quality of our representation, so if we increase our basis set size, we should get nearer and nearer to the ground state energy. But with the default values, this is the black curve actually, we see this behavior here. So at some point we change the curvature of this curve, and we go down to lower and lower energies. And of course this is not what we want. It is the case because the LAPW basis is nearly linearly dependent. And if we increase Kmax, at some point this linear dependence becomes numerically relevant, and then our overlap matrix becomes nearly singular, and then we end up in this regime where we get to lower and lower energies, and if we would increase Kmax even to higher values, we would get an error. So what can we do about that? There are simple things we can do. So it may help to increase the Lmax value then, and there we are at this red curve. Yeah, so we see if we increase Lmax, then we don't see this dip in the total energy, but the total energy becomes very, very stable. Yeah, and another thing we could do is we could reduce the Maffei-Tin radii. So this is the green curve here, and there I did not increase this Lmax, but you see reducing the Maffei-Tin radius means that we actually need larger Kmax values. So this is in agreement with this equation that we had, that we should choose Lmax equals Kmax times R Maffei-Tin, and that should be about 8 to 12. Yeah. So, but in the end, we end up with similar total energies once we have converged the calculation. So, let us now discuss the choice of the Gmax and Gmax-XC values. These are the cutoff parameters for the plane wave expansion, for the density, for the potential, and also for the step function. So the step function actually indicates where the interstitial region is. So of course we need a cutoff parameter there, because some of these quantities have infinitely many plane wave coefficients. For example, this potential, this plane wave expansion of the potential, and also the step function. And when we look at this expression for the interstitial contribution to the Hamiltonian matrix, we see that both of these quantities enter in this expression, and we have 2 times infinitely many plane wave coefficients, so we have to have some cutoff there. Yeah, so it should really have an effect, but in the end, turns out if we choose the cutoff according to this rule here, then we have very stable results. So Gmax should be larger or equals than Gmax-XC. So Gmax-XC is some reduced cutoff for the exchange correlation part of the potential, and this should be larger than 2 times Kmax. And typically we choose Gmax equals 3 times Kmax and Gmax-XC equals 2.5 times Kmax. So let us also discuss the energy parameters. These are not selected directly by the user, but we have an automatic method of choosing them. So let me first discuss what we actually plot here in this plot on the right side. So there I show the total energy depending on the energy parameter. And you see that I marked here 2 special energy parameters, so the atomic energy parameter and the energy center of mass method. And these are 2 ways of determining the energy parameter automatically. We typically use this atomic energy parameter, where we solve an auxiliary problem with some isolated atom that has the effective potential, the spherical part of the effective potential in the Maffei-Tin sphere, and an confining potential outside the sphere. And there we look for the eigenvalues of certain states and choose these eigenvalues as our energy parameters. So what we see is this energy parameter that we choose there is far away from the optimal energy parameter, that here would be like minus 0.15 Hartree. But even if we would choose this optimal energy parameter, we would not get the optimal total energy. So optimal total energy is down here, and you see this red curve also. So there I added some higher derivative local orbitals to our basis set, and with this our calculation gets more or less identical total energies independent of the exact choice of the energy parameter. Of course, this is an example for FCC cerium where this linearization error that we actually see here is pretty large, and for most systems it is much smaller. So now let us also discuss the choice of the muffin tin radii. And here we can say that there is no optimal choice. The muffin tin radii that we can choose depend on the chemistry in the unit cell and on the material in general. So if we have some very small bond lengths, then we have to use smaller muffin tin radii, otherwise we can use larger muffin tin radii. And there are also advantages to both larger muffin tin radii and smaller muffin tin radii. So for the large muffin tin radii, the calculations are faster. We saw that with the Kmax convergence, so we can choose smaller Kmax values, and this means our basis set is smaller, and then the calculation is faster. Otherwise, we have a larger linearization error there, because the linearization error is within the muffin tin sphere. And if we have a large muffin tin sphere, we also may get a large linearization error. And of course, if we use large muffin tin radii, we need fewer Semicore local orbitals. So it is less likely that our Semicore states reach out of the muffin tin sphere, and therefore we can describe them as core electrons. You should also keep in mind that certain quantities are only evaluated in the muffin tin sphere. So, for example, the magnetic moments that we associate with a certain atom or whatever. And there are also good reasons to choose smaller muffin tin radii, but this is here a bad reason. So first, the calculations are slower there, but on the other hand, they are typically much more stable. And we will get a smaller linearization error, but on the other hand, we need more Semicore local orbitals, but we have more space available for structural relaxations. So you see, there is no optimal choice here. It depends on what you want to calculate and how your material looks like. So let us discuss Semicore states and ghost bands in detail. So here I plot the band structure of BCC vanadium, and you see that I provide here the muffin tin radius that I use for the calculation, and I also write down how many electrons are lost, and with this we mean that the amount of electrons from the core electron states that reach out of the muffin tin sphere. And of course, this is kind of a measure to what extent this assumption that entered our orthogonality proof that we had in the previous talk is fulfilled. So if this number becomes large, this assumption is kind of broken. And if it is small, everything is okay. You can actually look for this quantity in the out or the out.xml file. They are named like slightly different. I think lost electrons is actually the name in the out.xml file. So now what happens if I reduce the muffin tin radius? Then we get this. So here I reduce the muffin tin radius to 2.2 Bohr, and you see that more electrons from the core reach out of the muffin tin sphere, and we get some strange and bizarre band that looks like an error at about 13 eV above the Fermi energy. And this is actually a ghost band. So what we see here is, first, this ghost band has nearly no dispersion, so it's kind of flat, and also we see that it is kind of damaged, so it has these jumps around when you go from one K point to the next K point. Actually, these jumps always appear if you want to represent a state and the representation is not very good, because our LAPW basis depends on the k point, and from k point to k point the basis set size may slightly change, and in such a case we will get such a jump here. So now what happens if I reduce the muffin tin radius even more? Then this ghost band comes down even more, and then I reduce it even more, and it comes even more down. And what I did not yet tell you is what this ghost band actually is. So I calculate here BCC vanadium, and BCC vanadium has a 3p semicore state. And in this example, I decide to treat this 3p semicore state as a core electron state. And but what we see here is some kind of a representation of this 3p state that comes out in our from our LAPW basis representation. So let us reduce the muffin tin sphere even more, and then we end up with an error. So now we get this error differ2, and it is there because suddenly this ghost band becomes occupied, and then of course we get some occupation of that state within our from our valence electrons, and it is also occupied by our core electrons, and of course this is unphysical, and this means we mess up our potential and everything breaks down. Actually, that is also what this error message means. So differ2 essentially means we messed up our potential. And unfortunately, this does not directly indicate that we have a ghost band. So I showed you this example with this Kmax convergence in the beginning, and if we increase the Kmax value parameter ever more in that example, we also get an error, and this is also differ2. And the other unfortunate thing is that also other error messages are possible in this case. So there are some error messages that essentially mean you messed up your potential. Differ2 is one of them, and then you should look like if there are ghost bands, or if your LAPW basis is kind of linearly dependent or whatever. Yeah. So you also see that in this example we lose like 12% of an electron from our core electrons, and keep this number in mind. So typically ghost bands are not a problem as long as you are below a few percent of an electron that are lost from the core, but I would say if you are in the range of 3 or 4 percent of an electron that you lose from the core, then you may want to check your calculation and see whether this actually is a problem or not. So what we do now is we take the 3p state out of our core electron description and put it into our valence electron description, and add a local orbital that describes this 3p states nicely, and then we end up with a nice band structure. That is how it should look like. You see, this is I chose here the second smallest muffin tin radius that we have tested, and only about 1% of an electron is lost from the core here, and everything is okay. Now let us discuss the linearization error. So what I plot here is the linearization error in terms of a representation error. So I try to represent a state at a certain energy with the description that is that we get from our LAPW basis. Yeah, and I look at different types of basis sets. So the black line is our conventional LAPW basis, and the red line is an LAPW basis that is extended by these higher derivative local orbitals, and then we can also add 1 or 2 sets of higher energy local orbitals. And you see this behavior here. So within the vicinity of our energy parameters, the representation of all the states is always good. But if we go farther away, you see that the representation gets worse and worse. But if we include some local orbitals, the representation stays very, very well. We also see here that the improvement of our representation with these higher energy local orbitals is kind of directed. So there we actually improve the basis set in the direction of the unoccupied states. And if we go to these lower states, lower energies, then we see this peak here. And so there is some state that we actually cannot nicely represent with our basis. And this is very good because in this example, this is the 4D core electron state. And our LAPW basis should be orthogonal to that. And we see that this actually is also fulfilled. But in our BCC vanadium example on the right-hand side, we have a similar situation. And here I show you the states relative to our 4p energy parameter. And here we have this 3p state that we just saw in the last slide. And you see that our representation of this state is, well, there is some finite representation of the state. We don't get a peak that goes up to 1, but we get kind of a shoulder at 0.6 here. And of course, if we improve the representation of the state, it will become a problem. So we have to represent this as a valence electron with an additional local orbital. So of course, this representation error is kind of theoretical. So let us look at more physical quantities. So here I plotted the equilibrium lattice constant for 2 materials, so FCC cerium and rock salt potassium chloride. And I plotted this in dependence of the muffin tin radius that we have. And of course, the equilibrium lattice constant should not depend on the muffin tin radius. But if we use the conventional LAPW basis, we actually see that there seems to be some dependence there in both materials. And this is due to the linearization error. So here we see if we reduce the muffin tin radius from our 3 Bohr radii to 2.4 or so, the lattice constant is changes by 1.6%. So this is quite a lot. Yeah. So there we are also in the ballpark of the difference between LDA and GGA or so. Yeah. And for potassium chloride, this lattice constant still changes like 0.4%. But if we add local orbitals to our basis set, then our lattice constant is more or less independent of the choice of the muffin tin radius. So this is also some kind of a quality criterion. So if the values that you calculate are independent of artificial numerical parameters, this is an indicator that your values are nicely converged and everything is okay with your calculation. So let me mention again, of course I show this linearization error here, but of course I choose some very extreme examples. So for most materials you actually will not see such a dependence on the muffin tin sphere radius, and the linearization error will be much smaller. So let me show you one more example. Of course, we typically choose our energy parameter such that we can nicely describe the occupied states, because they are used in the construction of our charge density, and the unoccupied states are not so important for us. Well, in general, or typically, but there are also cases where these unoccupied states become important. So for example, if we want to plot a band structure, or if we want to do some GW calculation on top of a DFT calculation. And then these states should also be nicely represented, but of course our energy parameters are far away from these states. So for example, here in potassium chloride, we see that the band gap can be reduced by 4% if we add these higher derivative local orbitals to the LAPW basis. And we see an even larger effect in FCC argon, and here the band gap can be reduced by 19% if we add local orbitals to our representation. So with this, let me end the talk and conclude the talk. So I showed you how to choose parameters like Kmax, Lmax, L non-spherical, the muffin-tin radii, Gmax and Gmax-XC. I also showed you that there is no perfect choice for this energy parameter, but all shortcomings that are due to suboptimal choices here can be overcome by adding local orbitals to the basis. Then we discussed how to deal with Semicore states and ghost bands, and I showed you the linearization error for some extreme cases, and I again did not discuss general numerical DFT parameters like the K-point set or the Fermi smearing. Of course, these are also cutoffs, so you should increase your K-point set until your calculation results are stable, and you should reduce the Fermi smearing until it is stable. But this is not directly connected to LAPW, and you have this in all DFT codes. And with this, I would like to thank you for your attention, and bye-bye.